Antennas, radiation pattern, series on antennas and wave propagation, lecture number 1.18. Antennas, while transmitting, are essentially radiators emitting radiation. Radiation is associated with certain characteristics like field intensity, power density, polarization, etc. Radiation pattern is a representation. It may be analytical representation or it may be graphical representation of variation of one or other characteristics, properties of radiation with the direction. Pattern, radiation pattern is quite an important aspect as far as antennas are concerned. In the present session, we focus on the study of radiation pattern and understanding of various aspects of the pattern. Let us start the session. Radiation pattern. Radiation pattern is also known as antenna pattern of an antenna is defined by IEEE as a mathematical function, means analytical expression or a graphical representation, a picture of radiation properties of antenna as a function of space coordinates. Space coordinates means pattern describes how one or other properties of the radiation of a radiator varies in space with the distance, with the direction. In most cases, the radiation pattern is determined in the far field region and is represented as function of directional coordinates. Notice in antenna theory, spherical coordinate system is used far more frequently than any other coordinate system. The coordinates of spherical coordinate system are r, theta, phi. R is radial coordinate, theta and phi. Theta is polar coordinate and phi is azimuthal coordinate. Theta, phi together, they are called directional coordinates. So pattern is most of the times function of theta and phi. Radiation properties include field intensity, radiation intensity, directivity, phase or polarization. Hence, radiation pattern is a general term as it can denote field pattern, power pattern, phase pattern, or even polarization pattern. But most important and widely used patterns are field pattern and power pattern. After these two, it is a polarization pattern that is used. Phase pattern also is used in the design, in the analysis, in the measurements of antennas. Now, a few terms are explained. These terms pertain to radiation patterns: amplitude pattern, phase pattern, power pattern, polarization pattern. What is amplitude pattern? Magnitude of E in different directions. Amplitude pattern is a representation. It may be analytical, may be graphical, but basically it gives information pertaining to magnitude of E in different directions. Phase pattern gives phase of E in different directions. Power pattern gives power or square of E in different directions. Polarization factor pattern gives orientation of E in different directions. Usually, all these patterns, they are given with respect to a particular radial distance. The distance is fixed, r is fixed. In different directions, how amplitude varies. That information we can have from amplitude pattern. How phase varies. That information from phase pattern. How power varies. That information from a power pattern. How polarization varies. That information from polarization pattern. It seems this IE is superfluous, so we can discard. Radiation patterns can be computed or measured for an antenna both when it is transmitting as well as receiving. So patterns can be computed, patterns can be measured for an antenna when it is in transmitting mode as well as when it is in receiving mode. But it is found theoretically as well as experimentally that for an antenna, the patterns obtained when transmitting is the same as that obtained when receiving. So pattern becomes 1 for an antenna when pattern of antenna when it is transmitting is the same as a pattern when it is receiving. Naturally, pattern becomes 1 for an antenna. Hence, the patterns of antennas do not depend upon whether it is transmitting or receiving. Some more points regarding radiation pattern. It is convenient to specify directional properties of the antenna in a spherical coordinate system. This fact has already been mentioned. In antenna theory, it is a spherical coordinate system that is used more frequently than any other coordinate system. Spherical system is associated with three coordinates, space coordinates. They are r, theta and phi. R is distance coordinate. It is called radial coordinate. Theta is polar coordinate. Phi is azimuthal coordinate. Theta and phi together denote capable of denoting direction in a unique manner. Now, new terms, plane patterns. What are plane patterns? These are two-dimensional graphs, whereas space patterns are three-dimensional representations. When we consider an antenna, we can easily notice that it is a three-dimensional entity and its radiation is also a three-dimensional spatial phenomenon. So a representation of radiation property also naturally becomes a three-dimensional spatial entity. They are called three-dimensional entities are called space patterns. But space patterns are difficult to put on paper. Paper is a three-dimensional plane. So three-dimensional entity cannot be put on a two-dimensional plane. Then how to overcome this difficulty? It is done. It is overcome with the help of resorting to plane pattern representation of space patterns. Plane patterns are two-dimensional graphs, whereas space patterns are three-dimensional representations. As three-dimensional space patterns are difficult to be sketched in two-dimensional paper, plane patterns come into being. Usually, the patterns in certain planes which are capable of giving more information called principal planes are considered. So here the point is pattern is not considered in any arbitrary plane. Only in certain planes the patterns are considered. The planes in which the pattern is able to give good amount of information. Only that planes are considered to sketch or to find two-dimensional plane patterns. Those planes are called principal planes. So principal plane patterns give good amount of information than plane patterns in any other plane. The patterns in the principal planes give as much information as space patterns. So two aspects are there to understand here. Principal plane patterns give more information than plane pattern in any other plane. This is one aspect. Second aspect is principal plane patterns, even though they are two-dimensional, they are able to provide as much information regarding radiation as provided by three-dimensional space patterns. Some information regarding the principal plane patterns. The principal E-plane is defined as plane containing the electric field vector and direction of the maximum radiation. And the principal H-plane is the plane containing the magnetic field vector and the direction of maximum radiation. Here, principal planes are defined. Principal E-plane is defined, principal H-plane is defined. Once this principal E-plane and principal H-planes are defined, the pattern in these planes becomes principal plane patterns. The plane patterns in the planes containing E-plane and H-plane are called principal plane patterns. Azimuthal and elevation cuts, these are also plane patterns. The pattern with the azimuthal angle phi as a variable for fixed polar angle theta is called azimuthal or conical cut, and it is basically a horizontal plane pattern. The pattern in the theta plane for a fixed phi is called elevation or great circle cut. It is vertical plane pattern. So till now, while going through the two slides, this slide and the previous slide, we come across terms like space pattern. Space pattern is the real pattern, actual pattern, but it is three-dimensional one. We also come across a plane pattern. The term plane pattern is one which can be put on a piece of paper, a two-dimensional one. It represents the space pattern in certain planes. We also come across principal plane patterns. Plane patterns in principal planes or principal plane patterns. The importance of principal plane patterns is that they are able to give information as much given by space patterns. Two types of principal planes are there. Principal E-plane, principal H-plane. These two are defined. The plane pattern in principal E-plane is principal E-plane pattern. The plane pattern in principal H-plane is principal H-plane pattern. Apart from that, we also encounter in antenna theory azimuthal and elevation cuts. Azimuthal or conical cut is a horizontal plane pattern, whereas elevation or great circle cut is a vertical plane pattern. Now, an information, serious information pertaining to field pattern. Field patterns are two types, polar, rectangular. If we use rectangular coordinate system, then it is a rectangular field pattern. If we use polar coordinate system, spherical coordinate system, then it is polar field pattern. Okay, two types are there again, Plane patterns, space patterns. Plane patterns are two-dimensional, space patterns are three-dimensional. In plane patterns, E-plane pattern, it is vertical plane pattern. H-plane pattern, it is horizontal plane pattern. Azimuthal cut, it is horizontal plane pattern. Elevation cut, it is vertical plane pattern. E-plane pattern and H-plane pattern, these two are considered as principal plane patterns. In space patterns, we encounter these types: broadcast pattern, pencil beam pattern, fan beam pattern, shaped beam pattern. These are all types of three-dimensional patterns given by different antennas. Some more information regarding radiation patterns. Omnidirectional or broadcast type of pattern. Antennas with this type of pattern are used for broadcasting or for services where all directions are to be covered equally. These antennas usually have non-directional horizontal patterns while the vertical patterns are directional. An example for omnidirectional or broadcast type of pattern giving antenna is half-wave dipole. When it is excited, half-wave dipole radiates equally in the same way horizontally, in a horizontal plane like this, equally well in all directions, in horizontal plane, omnidirectional. Of course, this equality, sameness is only in horizontal plane. When we consider a vertical plane, the pattern is like this, dumbbell shape. Pencil beam pattern, a radiation pattern with relatively narrow and equal beam widths in both the principal planes is called pencil beam pattern. It is a highly directional pattern concentrating the radiation in a very narrow angular sector, giving a maximum directivity. Another shape of a pattern we encounter frequently is a fan beam. A pattern of main beam having a narrow beam width in one plane and much broader beam width in the orthogonal plane is referred to as fan beam pattern. It is similar to pencil beam pattern except that the beam cross sections elliptical rather than circular. Section is elliptical rather than circular. This beam also implies substantial amount of gain. This is fan beam. Shaped beam pattern. When a specific type of coverage is required in one of the principal planes like cosecant type of pattern, then antennas with the shaped beam patterns are used. In the other principal plane, the pattern may be a pencil beam or circular. Here is shown pattern and its parts. This is main beam. Center is indicated as bore site, direction of center. Half power beam width is indicated 0.7072 to 0.707. One point is in the upper half, another is in the lower half. First null beam width is also indicated. Side lobes, first side lobe, second side lobe, third side lobe, fourth side lobe, like that several side lobes. Side lobes are also called minor lobes. Between two lobes, there exists a region where there is no radiation. That region is called null region. So this is first null, second null, third null, fourth null, like this. Before going further, one point is required to be mentioned here. The actual three-dimensional space pattern. As it is, we are seeing two-dimensional plane pattern. Three-dimensional actual pattern, space pattern, can be obtained by rotating this pattern around its axis or around its bore site by 180 degrees. The surface of this pattern sweeps, traces a three-dimensional geometrical entity. That actual represents space pattern of the antenna. Some more points regarding the pattern. Regions of relatively weak radiation intensity are called nulls, whereas regions which represent presence of radiation of the pattern are called lobes. The lobe is always bounded by nulls. Two types of lobes are there: major or main lobe or principal lobe, and minor or side lobe. So major lobe, main lobe or principal lobe is the lobe which contains the direction of maximum radiation or bore site. An antenna may have more than one major lobe. Back lobe is the lobe whose axis makes 180 degrees with the axis of the major lobe, and the side lobes are lobes whose axis make angles less than 180 degrees with the axis of the major lobe. Back lobe and side lobes together are called minor lobes. So major lobes, minor lobes. Minor lobes usually indicate the wastage of energy. They are unwanted. Major lobe is usually one, but sometimes one can have more than one or two. Some more terms pertaining to pattern. Half power beamwidth is angular separation between half power points of the major lobe. It is defined as in a plane containing the direction of maximum of the beam, the angle between the two directions in which radiation intensity is one half the maximum value of the beam. This is the basic definition of half power beamwidth. The angular separation between the first nulls that surround the major lobe is first null beamwidth. The width of the beam is an important aspect, important parameter. Sometimes it requires, in some applications, it is essential for the beam width as small as possible. It is specified either by half power beam width or by first null beam width. A little bit of calculations, computations shows us that first null beam width is roughly equal to twice half power beam width. Now, normalized patterns. What are normalized patterns? These are ones in which field strength or radiation intensity, whichever is used to sketch the pattern, is normalized with respect to its maximum value. Normalization is the term we come across in transmission line theory, in antenna theory, and in some other areas of study too. In antenna theory, normalization refers to dividing a particular impedance by the characteristic impedance of the line. So normalization is done with the characteristic impedance of the line in transmission line theory. Here in antenna theory, normalization is with respect to the maximum value of field strength or radiation intensity. In transmission line theory, normalization is impedance normalization. Here in antenna theory, normalization is field strength normalization or radiation intensity normalization. That difference one has to keep in mind. Let us move to another aspect pertaining to antennas. So far, our discussion is concerned with the patterns, radiation patterns. Now, we are entering into another aspect of antennas, that is antenna bandwidth. This is also an important parameter, performance indicator of antennas, bandwidth. In case of antennas, bandwidth is defined in a very specific way while conforming to the general definition. For antennas, it is the range of frequencies within which the performance of the antenna with respect to some characteristic conforms to a specified standard. Seems it is conform. The characteristic can be pattern or impedance or some other antenna parameter, and hence several bandwidths have come into being for antennas, as many as number of antenna parameters. Pattern bandwidth, impedance bandwidth, directivity bandwidth, polarization bandwidth, efficiency bandwidth. These are most widely used bandwidths in antenna theory. Directivity and efficiency bandwidths together are often referred to as gain bandwidth. Here is shown in the form of a diagram various bandwidths: directivity, gain bandwidth, polarization bandwidth, axial ratio bandwidth, impedance return loss bandwidth, efficiency bandwidth, pattern bandwidth. So many bandwidths are there when it comes to antenna theory. A brief description explanation is given regarding these bandwidths here. Pattern bandwidth, this is one which is defined with respect to radiation pattern. Impedance bandwidth or return loss bandwidth, this is the frequency range wherein the structure is satisfactorily usable, exhibiting certain impedance, usually 50 ohms. Impedance bandwidth depends on several parameters related to the antenna itself and the type of feed used. Several vendors use different definitions of impedance bandwidth, such as VSWR equal to 2:1 S11 scattering parameter. Values other than minus 10 dB, etc. Only impedance bandwidth is specified and used most of the times. Here it should be lesser than S11. S11 actually represents reflection quotient or a value related to reflection, representing the amount of mismatch. Mismatch should not be more than minus 10 dB of S11. Now, directivity and gain bandwidth. This is the frequency range wherein the antenna meets a certain directivity gain requirement. Example, 1 dB gain flatness. Efficiency bandwidth. This is the frequency range over which the antenna has reasonable application dependent radiation or total efficiency. Polarization bandwidth is the frequency range wherein the antenna maintains its stipulated polarization. Axial ratio bandwidth, this bandwidth is related to polarization bandwidth, and this number expresses the quality of the circular polarization of an antenna. Axial ratio is 1 for circular polarization. Deviation of axial ratio value from 1 gives an indication regarding the deviation of polarization of the antenna from a true or perfect circular polarization. With this, we come to an end of this session. In this session, two aspects pertaining to antennas are considered. One is a radiation pattern, another is antenna bandwidth. Both are quite an important parameters determining the performance of antennas. Hope this session is useful to you. We meet again in another session with a new topic soon.